Welcome to Talk Tensors.
Glad to be here.
It is incredibly great to have you with us for today's deep dive. If you've been monitoring the model registries, Hacker News, or the X machine learning community over the past week, you already know exactly what we're focusing on today.
Oh, absolutely. It's been everywhere.
Right. I mean, your timeline has likely been completely flooded with benchmark charts, loss curves, and just a lot of intense debate about this brand new, highly trending open weight model series.
Yeah, you really couldn't escape it if you tried.
No, you couldn't. And we are talking about a release that is fundamentally shifting the discourse in the AI engineering community. It's the kind of release that makes researchers just stop what they are doing, pull down the weights, and immediately start benchmarking on their own local clusters.
Which is exactly what we've been doing for the last few days.
Exactly. So for you listening, grab a coffee and settle in, because we are going to get into the absolute thick of the technical architecture today. We are looking at a model family that spans from highly optimized 0.5 billion parameter models designed for edge inference, all the way up to a 72 billion parameter monolithic dense model.
And we can't forget the mixture of experts architecture in there too.
Yes, exactly, alongside a highly unique 57 billion parameter mixture of experts architecture.
And the current wave of attention this release is getting is, well, it's absolutely justified by the underlying engineering.
Yeah,
completely. What we are observing with this specific model family is a tangible bridging of the performance gap. And I mean the gap between open weight architectures models that developers can actually download, modify, and run entirely locally, and the massive proprietary closed API systems.
like GPT-4 or Claude 3 Opus.
Precisely. Historically, the assumption within the field was that to achieve state-of-the-art multi-step reasoning, or complex code generation, and robust multilingual performance, a developer was basically forced to operate behind an enterprise API paywall.
Right, you were entirely reliant on centralized server farms.
Exactly. But this release fundamentally shatters that assumption. It proves that highly curated data and rigorous architectural optimization can allow open weight models to hit those exact same performance thresholds.
And that is exactly why we are dedicating this entire deep dive to it. Our mission today is to look right past the high-level social media buzz and unpack the actual granular engineering that makes this paradigm shift possible.
We need to get into the weeds.
We do. We want to understand the matrix operations, the meticulous data curation pipelines, the novel reinforcement learning recipes, and the real-world implications of these performance benchmarks.
Because that's what matters to the people actually building with this.
Exactly. We are going to explore why this matters so intensely to practitioners building production applications right now. Because ultimately, this redefines the boundaries of what is computationally viable on local consumer GPUs and constrained edge devices for you, the developer.
It's a complete game changer for local deployment.
Okay, let's unpack this. Before we even look at the transformer layers, we have to examine the tokenization strategy.
The tokenizer is always where it starts.
Right, because the foundation dictates the memory efficiency of the entire system.
It does. And the tokenization layer is frequently overlooked in high-level discussions, but it is the primary bottleneck for multilingual throughput.
So what do they do differently here?
Well, the engineering team here deployed a byte-level light pairing coding scheme, or BPE. The standout metric is the vocabulary size, which sits at exactly 151,643 regular tokens.
Plus specific control tokens, right?
Yes, supplemented by specific control tokens. Now, when you compare that against earlier architectures that typically bottlenecked around a 32,000 or maybe a 50,000 token vocabulary, extending to over 150,000 represents a massive expansion of the embedding matrix.
But a larger embedding matrix obviously increases the parameter count right at the input and output layers.
Significantly, yes.
Which requires more VRAM just to load the model into memory. So there has to be a significant computational payoff for expanding the vocabulary that widely. I imagine this heavily impacts the compression rate, particularly for non-Latin scripts.
That's exactly it. The computational payoff is immense when evaluating autoregressive generation speeds. What's fascinating here is how that highly optimized compression rate directly translates to superior multilingual capabilities while simultaneously defending the context window.
Defending the context window. I like that phrasing. How does a small vocabulary attack the context window?
Well, when a model operates with a constrained vocabulary, it is heavily biased toward English. Consequently, when it encounters complex morphological structures in languages like Arabic, Russian, or Vietnamese, it is forced to fracture those words into numerous arbitrary subword byte fragments.
Because it doesn't have a single token for a common Vietnamese word, so it just chops it up into tiny phonetic pieces.
Exactly. A standard sentence in Thai might consume 30 or 40 tokens on a legacy English-centric tokenizer, whereas an English sentence of the exact same semantic weight might only use 10 tokens.
And since the core self-attention mechanism scales quadratically with sequence length, feeding a transformer 40 tokens instead of 10 doesn't just use a little more memory.
No, it exponentially increases the FOPs required for that specific forward pass.
Right.
By expanding the vocabulary to 151,643 tokens, the tokenizer establishes native representations for entire words or large semantic chunks across approximately 30 different languages.
That is massive.
It is. It successfully encodes complex semantic concepts in Chinese, Japanese, French, or Arabic into single discrete tokens. This drastically reduces the sequence lengths required to process non-English inputs.
So for a practitioner, what does this actually look like in deployment?
For a practitioner, this means the model processes these languages natively without rapidly saturating the KV cache. You preserve the memory footprint, which allows you to maintain high batch sizes and execute much longer, more complex document retrieval tasks across diverse linguistic datasets within the exact same hardware constraints.
You are basically packing significantly more semantic density into every single position of the context window. That makes the decision to eat the parameter costs at the embedding layer entirely worth it.
Without a doubt.
Now, stepping up from the tokenizer, let's look at the dense model variants, the 0.5B, 1.5B, 7B, and 72B architectures. A critical optimization deployed across this entire dense stack is grouped query attention, or GQA.
Yes, GQA is essential here.
I know GQA has become somewhat of a standard over the last year, replacing multi-head attention to save memory. But I want to get into the hardware-level mechanics of why it's so vital for the 7B and 72B models specifically.
To understand the hardware implications of GQA, we need to look at where the actual latency occurs during LLM inference. During autoregressive decoding, the phase where the model is actually generating tokens one by one, the process is rarely compute-bound.
Really? Even for a 72 billion parameter model?
Yes. The matrix multiplication units on modern GPUs are incredibly fast. The actual bottleneck is memory bandwidth. Inference is heavily memory-bound. In traditional multi-head attention, for every single query head the model projects, it must maintain a distinct key head and value head.
Right, the KV cache.
Exactly. All of these key and value tensors from previous tokens must be stored in the GPU's high bandwidth memory, or HBM, to provide context for the next token, that is the KV cache.
And as the sequence length grows, or as you increase the batch size to serve multiple users concurrently, that KV cache just balloons in size.
It grows linearly with every token and every user.
So the GPU has to constantly swap those massive KV tensors from HBM into the SRAM of the streaming multiprocessors for every single token generated. That data movement is what actually throttles the tokens per second throughput.
You've identified the exact bottleneck. Now, earlier architectures tried multi-query attention. MQA attempted to solve this by forcing all query heads to share just a single key and value head,
which shrinks the KV cache dramatically.
It drastically reduced the KV cache size, but the representational capacity of the attention mechanism degraded too severely, and that impacted reasoning quality. Grouped query attention provides the optimal Pareto frontier.
It's the middle ground.
Exactly. You divide the query heads into discrete groups. For instance, in a 64-head architecture like the 72B model, instead of computing 64 distinct key-value pairs, you might configure 8 key-value heads. Therefore, a group of 8 query heads shares a single key-value projection.
So you are reducing the KV cache memory footprint by a factor of 8, drastically cutting down the HBM bandwidth requirements during generation.
It fundamentally alters the deployment calculus. By optimizing the KV cache via GQA, developers can comfortably deploy the 7 billion parameter model on a standard consumer-grade GPU equipped with just 16 gigabytes of VRAM.
While simultaneously pushing larger batch sizes, right?
Yes, maintaining high-speed generation for multiple requests. You aren't constantly hitting the memory wall.
Beyond GQA, the engineering team integrated several other architectural refinements to stabilize training. They opted for SWGLU activation functions instead of GLU or traditional ReLUs. They implemented RMS norm for pre-normalization.
Which bypasses the heavy mean-centering computational overhead of standard layer norm.
Exactly. And they notably retained QKV bias in the attention mechanism. SWGLU and RMS norm are fairly standard in high-performance open weights now, but I want to touch on the QKV bias. A lot of models strip out bias terms in the linear layers to save on parameter count and compute. Why retain the bias specifically for the queries, keys, and values?
Stripping bias terms is a common optimization, yes. But empirical evidence increasingly shows that retaining the bias vectors in the QKV projections provides the attention mechanism with a crucial mathematical flexibility.
Flexibility to do what?
It allows the attention heads to better capture absolute positional offsets and baseline attention distributions that are independent of the specific token embeddings.
So it's not just looking at what the token means, but where it naturally sits.
Precisely. It essentially gives the attention matrix a learned default state to fall back on. This improves the resolution of the attention scores, especially in highly complex routing scenarios within the deep layers.
And when you combine that with SWGLU,
which provides a smoother, more complex gradient flow than GLU due to its gating mechanism.
And the computational efficiency of RMS norm, every micro-optimization here compounds.
It results in a model that converges faster during pre-training and executes with significantly lower latency during inference.
That compounding efficiency is exactly what allows them to push the context lengths to such extremes. Let's dig into the long context capabilities, because this is where the engineering gets aggressively complex.
The context window scaling is remarkable.
It is. The context window on these models scales from a baseline of 4,000 tokens during the initial pre-training phase, up to a staggering 131,072 tokens during fine-tuning.
Expanding a context window by a factor of 32 usually destroys the attention entropy.
Right. The model loses track of positional relationships and the loss spikes. To achieve this 131K context, they utilize dual chunk attention, or DCA, combined with a specific implementation of yarn. Let's isolate DCA first. How does dual chunk attention mathematically decouple local and global attention to handle a sequence that long?
The challenge with the 131,000 token sequence is the quadratic scaling of the attention matrix we mentioned earlier, computing the dot product of every single token against every other token in a sequence that long requires an astronomical amount of FLOPs in memory.
It's just computationally impossible for most setups.
Exactly. Dual chunk attention fundamentally re-architects how the sequence is processed. Instead of one massive, continuous matrix operation, DCA segments the input sequence into manageable chunks. When the model computes the attention scores, it evaluates the relationship between the queries and keys.
So if a query token and a key token exist within the same chunk, the operation proceeds identically to standard interchunk self-attention. It's highly localized and computationally cheap.
Correct. But the innovation lies in how DCA handles interchunk relationships. If the model needs to connect a concept from a chunk at the beginning of the sequence to a chunk at the very end, DCA modifies the positional indices.
How so?
It effectively captures the relative positional information across the chunk boundaries without forcing the model to compute the full dense attention matrix for all the intervening tokens. It isolates the local high-resolution attention computation from the broader global dependency tracking.
That is brilliant. This dramatically reduces the computational complexity while preserving the model's ability to pull information from anywhere in the 131K window.
Yes, but chunking the attention matrix only solves the compute problem.
Right. You still have to ensure the model actually understands the geometric distance between those tokens across 131,000 positions. To handle that, they manipulated the rotary positional embeddings, or ROPE.
Specifically, they shifted the base frequency.
They shifted it from the standard 10,000 to 1 million. For an audience familiar with ROPE encoding absolute positions by rotating the query and key representations in the complex plane, what does shifting that base frequency to 1 million actually do to the wavelength of those positional encodings?
Let's break that down. ROPE encodes positional information across different hidden dimensions using varying frequencies. The higher dimensions have very low frequencies, meaning their rotation angles change very slowly as you move through the sequence length.
Like the hour hand on a clock compared to the second hand.
Good analogy. When a model is trained on a 4,000 token context with a base frequency of 10,000, the lowest frequency dimensions have enough wavelength to uniquely distinguish token 100 from token 3,900. The relative dot products remain distinct.
But if you push past 4,000,
if you naively extrapolate that same base frequency out to 131,000 tokens, those low-frequency dimensions complete their rotations. They loop back around. The positional encodings begin to alias.
meaning the dot products of the queries and keys at distant positions decay into uniform noise, and the model essentially goes blind to the order of tokens beyond its initial training length.
Exactly the problem. By shifting the base frequency to 1 million, you drastically expand the wavelength of the lowest frequency dimensions. You stretch the positional embedding space.
So it takes much, much longer for the rotation to complete a full cycle.
Precisely. This ensures that even at token position 120,000, the rope E rotations remain unique and have not wrapped around to alias earlier positions. The model maintains high-resolution tracking of exactly where every token resides. Furthermore, this base frequency shift is coupled with yarn,
which stands for yet another ropey extension method.
Yes. Yarn applies a temperature rescaling equation to the attention logits based on the sequence distance.
Right, because even if the positional encodings are unique, expanding the sequence length means a single query token is now taking the softmax over 131,000 keys instead of just 4,000.
That massive denominator in the softmax operation naturally dilutes the attention scores,
causing attention entropy to spike. The model's focus becomes too diffuse, and it starts hallucinating or ignoring specific facts.
Yarn prevents that diffusion. By applying a temperature scaling factor directly to the pre-softmax logits, Yarn artificially sharpens the attention distribution. It counteracts the entropy introduced by the massively expanded context window.
So the combination of DCA managing the compute complexity, the 1 million base frequency stretching the positional wavelengths, and Yarn dynamically rescaling the attention logits creates a system that remains highly coherent regardless of whether it's processing an abstract or an entire code base.
That is a perfect summary of the long context engine.
So those dense model optimizations, GQA, SWGLU, DCA, and Yarn, explain the incredible throughput and context capabilities of the monolithic models. But the real architectural paradigm shift in this release isn't just the dense models, it's how they approached conditional computation.
The mixture of experts architecture.
Let's examine the 57 billion parameter mixture of experts, or MOE variant. That headline metric is fascinating. It possesses 57 billion total parameters, but it only activates 14 billion parameters during the forward pass for any given token.
This fine-grained design fundamentally diverges from earlier open-weight MOE architectures. The evolution of mixture of experts routing is moving rapidly.
The core premise of MOE being sparse conditional computation. You don't need to push every token through the entire parameter space to achieve a high-quality representation.
Correct. However, early open-weight MOE implementations often took a very blunt approach. They would take a standard dense transformer block, duplicate the feed-forward network into, say, 8 massive experts, and use a simple top-2 routing mechanism.
It was a very coarse division of labor. You had a few massive experts handling broad swaths of the latent space. But the engineering team here rejected that setup.
They did. Instead of 8 massive experts, this model relies on 64 highly specialized, fine-grained experts. And for any given token, the gating network routes to 8 of them simultaneously.
But the most intriguing architectural decision is that alongside those 64 routed experts, they implemented 8 shared experts that process every single token, regardless of the routing probabilities.
Yes, the shared experts are a massive innovation here.
What is the mathematical advantage of permanently dedicating parameter capacity to shared experts?
The inclusion of shared experts addresses a significant inefficiency in traditional MOE routing. In a standard MOE, every expert is forced to dedicate a portion of its parameter capacity to learning universal, foundational knowledge.
Like basic grammar, common semantic structures, syntax rules.
Exactly. This is totally redundant. By isolating 8 experts as shared, you permanently allocate a subnetwork to process the universal representations required by every single token. These shared experts act as the foundational processing layer.
Which means the gating network doesn't have to waste bandwidth routing simple syntax tokens.
And the 64 fine-grained routed experts are freed from the burden of learning basic language modeling.
Precisely. The 64 routed experts can dedicate 100% of their parameter capacity to highly niche, specialized domain knowledge, whether that is C++ plus memory management, complex differential equations, or specific historical facts.
By decoupling the universal representations from the highly specialized representations, you dramatically increase the parameter efficiency of the active 14 billion parameters.
The model utilizes its active FLOPs far more effectively than a monolithic dense model of the exact same active size. Here's where it gets really interesting. Creating 64 highly specialized experts is easy in theory, but training them from a random initialization is notoriously unstable.
It requires an incredible amount of compute to get them to converge.
To bypass the massive compute costs of from-scratch MOE training, they utilized an upcycling methodology. They took the pre-trained weights from their heavily optimized 7 billion parameter dense model and mathematically transformed them into this 57 billion parameter MOE structure.
Upcycling is arguably the most elegant cost-saving mechanism in modern large-scale training.
How exactly do you surgically expand one pre-trained feed-forward network into 64 distinct experts without destroying the latent representations it already learned?
The math behind the transformation requires careful manipulation of the dense weights. To instantiate the fine-grained experts, they take the original feed-forward network weights from the dense 7B model and replicate them across the designated expert dimensions.
So if you need 64 experts, you just create 64 copies of the FFN layers.
Yes. However, if you simply copy them, you have 64 perfectly identical experts. The gating network, the router, would completely fail to differentiate between them because their output gradients would be completely symmetric.
Right. If all 64 experts output the exact same vector, the router never learns a preference. You have to break the symmetry. I've read about adding subtle Gaussian noise to the weights to break symmetry, but the approach they took here seems far more aggressive.
Much more aggressive.
They didn't just add noise, they shuffled the parameters along the intermediate dimension, and then for every single fine-grained expert, they randomly reinitialized exactly 50% of the parameters. They wiped out half of the pre-trained weights entirely.
They did.
That sounds like a recipe for catastrophic forgetting. What is the compute cost of recovering from a 50% loss of pre-trained knowledge, and why take such a drastic step?
It is an aggressive intervention, but it is a highly calculated shock to the system. The phenomenon you have to combat in MOE training is called expert collapse.
What happens during expert collapse?
In expert collapse, the gating network prematurely converges on routing the vast majority of tokens to just a handful of experts that happen to optimize slightly faster early in training. The remaining experts are starved of tokens and never receive gradient updates.
Effectively rendering them dead parameters.
Exactly. If you only apply subtle Gaussian noise during upcycling, the experts remain too similar and the router easily falls into this collapse state.
So by annihilating 50% of the parameters in each expert and replacing them with random noise, you deliberately cripple their generalized capabilities.
Yeah, you introduce a massive variance in their initial loss. Because 50% of their weights are random, they perform terribly on general tasks. The training process is violently forced into exploration mode.
It has to explore just to fix the damage.
To minimize the suddenly massive loss, the gradient descent algorithm forces the gating network to aggressively partition the latent space. The experts are compelled to specialize rapidly in highly narrow domains just to overcome the random noise injected into their weights.
That makes perfect sense.
While it does require a brief intensive phase of pre-training to recover the baseline performance, the resulting MOE architecture exhibits incredibly sharp, distinct routing boundaries. The specialists actually become specialists.
The controlled chaos of randomization forces the optimization landscape out of local minima. It's a brilliant, if initially terrifying, mathematical strategy. So the upcycling trick ensures the MOE architecture is highly specialized and computationally efficient. But a brilliant architecture is useless without knowledge.
Architecture is only half the battle.
Let's analyze the actual diet they fed these models, the pre-training data philosophy. The researchers curated a massive data set of over 7 trillion tokens with a heavy, deliberate over-indexing on raw code and mathematical data. The goal, obviously, was to boost the underlying logical reasoning.
The industry consensus has solidified around the idea that code and mathematics are not just separate domains of knowledge. They act as fundamental scaffolding for general reasoning.
Because they teach the model strict logic.
Yes. Training a model on the strict logical syntax of Python, or the sequential deduction required in geometry, fundamentally alters the model's latent space. It improves its ability to plan, to maintain strict logical consistency across long outputs, and to perform zero-shot deduction in entirely unrelated natural language tasks.
But the true contribution of this paper to the broader scientific community isn't the 7 trillion figure. It is their empirical findings regarding the scaling laws of data volume versus data quality.
This is the most fascinating part of the technical report.
They didn't just stop at 7 trillion tokens. They actively experimented with relaxing their heuristic data filters, the deduplication pipelines, the toxicity classifiers, the low-quality text heuristics to compile a massively extended dataset of 12 trillion tokens.
They wanted to see if more was inherently better.
They then ran ablation studies, training the larger architectures on both the 7 trillion high-quality set and the 12 trillion lower-quality set. And the results challenge a core tenet of modern AI development. How exactly did they measure the degradation when moving to the 12 trillion token dataset?
They monitored the loss curves and benchmark evaluations across the checkpoints. The prevailing theory for the last 3 years has been the simple scaling law.
Yeah.
Assuming the architecture is sufficiently large, simply feeding it more tokens will invariably result in lower perplexity and higher benchmark performance. Volume was king.
But their findings contradict that.
Completely.
Yeah.
Their ablation studies revealed that for the highest capacity models, the 72B dense and the 57B MoE training on the 12 trillion token dataset yielded diminishing, and in some metrics, zero improvement compared to the tightly curated 7 trillion token dataset.
If we connect this to the bigger picture, this implies we are actively hitting the asymptote of the just add more data era. If the data possesses high entropy but low semantic value, like auto-generated SEO spam, poorly structured logs, or highly redundant web scrapes throwing an extra 5 trillion tokens at the optimizer doesn't improve the model's representations.
The model simply wastes compute cycles memorizing noise.
Exactly.
High-quality curation, rigorous deduplication, and semantic diversity are now definitively more critical than raw token volume. The fact that the engineering team opted to intentionally discard 5 trillion tokens to protect the integrity of the primary pre-training dataset represents a massive philosophical pivot for the industry.
It signals the end of brute force scaling and the beginning of hyper-curated data engineering. That brings us directly into the post-training phase, the supervised fine-tuning, and the reinforcement learning from human feedback using direct preference optimization, or DPO.
The alignment phase.
Historically, the alignment phase is a massive bottleneck. You need thousands of human annotators writing prompts, analyzing 2 different model outputs, and manually ranking which one is better to create preference data. The human-in-the-loop requirement is inherently unscalable and introduces massive variance in data quality.
Because humans disagree, get tired, and make mistakes.
Exactly. To bypass this, the team deployed highly complex automated data synthesis pipelines. Let's dissect the execution feedback loop they use for code generation. This is where the model essentially acts as its own compiler and QA team.
Relying on humans to evaluate complex code generation is not just slow, it's prone to massive error rates. The execution feedback methodology completely automates the generation of pristine, mathematically verified preference data.
How does the loop actually operate?
Instead of a human reading the code, the model is prompted to solve a complex programming task. Crucially, it is also instructed to simultaneously write an exhaustive suite of unit tests for its own proposed solution.
So the model generates the code and the test cases. Then, an automated pipeline takes that output, compiles the code in a sandbox environment, and executes the unit tests.
It leverages the deterministic nature of code execution. If the code compiles and passes all unit tests, that entire generation path is automatically flagged as high-quality demonstration data for supervised fine-tuning.
And if it fails?
If the code throws a compilation error or fails a unit test, that output is categorized as negative preference data. The model physically executes its own hypotheses and learns directly from the deterministic success or failure of the compiler.
It creates a self-sustaining reinforcement learning loop that runs at the speed of the compute cluster, entirely free from human subjective bias or manual labeling delays.
It's essentially mimicking human trial and error, but at a massive parallelized scale.
But code is deterministic. Natural language instruction following is highly subjective. How did they automate preference data generation for complex natural language tasks? They use a technique called verification functions.
A very clever approach.
Suppose you give the model an adversarial prompt. Write an essay about the geopolitical impact of the microchip, but do not use the letter E. Ensure every paragraph starts with a vowel and make it exactly 400 words long. A human would take 10 minutes just to verify those constraints. How does the automated loop handle that?
For complex instruction following, they task the model to write isolated Python scripts, whose sole purpose is to verify constraint adherence.
The model writes the script to check itself.
Yes. The model generates the essay based on the prompt. Then, a separate subroutine runs the verification script, which simply checks the word count, scans for the letter E, and validates the starting characters of the paragraphs against the generated essay.
So if the script returns true across all constraints, the essay is added to the positive preference dataset. This allows them to scale constraint-heavy instruction tuning to millions of examples without a single human reviewer.
It's incredibly efficient.
I have to ask about the stability of the RLHF and DPO loops when bootstrapping data like this. When a model trains on its own synthetic outputs, there is a known risk of model collapse or reward hacking, where the model discovers a degenerate shortcut that satisfies the verification script but produces unreadable gibberish.
Reward hacking is the primary failure mode of automated synthesis.
How do you prevent the DPO loss function from optimizing for these degenerate edge cases when humans aren't checking the data?
To stabilize the DPO loop, they utilized a rigorous rejection sampling methodology, particularly in mathematical and logical reasoning tasks. Instead of accepting the first output that passes verification, the model is forced to generate a massive distribution of potential reasoning paths.
Sometimes tens or hundreds of distinct step-by-step deductions for a single problem.
They only retain the paths that arrive at the correct final answer, but more importantly, they apply perplexity filters and length penalties to the intermediate reasoning steps.
So they penalize the model if it tries to cheat the verification by generating unnecessarily long looping logic, or if it outputs low probability gibberish that somehow happens to contain the correct final variable at the end.
Precisely. By aggressively pruning the synthetic data distribution, and maintaining a strict threshold on the grammatical and logical coherence of the intermediate steps, they prevent the DPO algorithm from falling into degenerate local optima.
They also utilize an incredible technique called data repurposing to synthesize high-quality role-playing and persona data, which is notoriously difficult to automate because it requires creative nuance.
Creating highly skilled literary writing or distinct historical personas usually requires hiring creative writers.
You can't just write a Python script to check if a model sounds perfectly like a 19th century aristocratic vampire. So they script Wikipedia for incredibly detailed character profiles, historical biographies, and linguistic traits.
They used factual profiles as the creative constraints.
They instructed the model to synthesize massive conversational datasets based purely on the rigid constraints of those factual Wikipedia profiles. It acts as a massive reading comprehension and extrapolation task, ensuring the synthesized dialogue stays structurally faithful to the character's known traits without requiring human authors to write a single line of dialogue.
It is a remarkable engineering pipeline. When you combine the execution feedback for code, the verification functions for constraint following, the rejection sampling for math, and the data repurposing for personas, you establish a training regimen where the model is actively bootstrapping its own intelligence.
It represents a fundamental shift from human-in-the-loop to model-in-the-loop alignment. Okay, we have thoroughly analyzed the engine room, the MODI routing mechanics, and the automated data synthesis pipelines. Now it is time to look at the actual output. Let's analyze Section 4. The report card.
The benchmarks.
We need to evaluate the rigorous benchmarks and real-world performance, starting with the heavyweight clashes. We are talking about the 72 billion parameter base and instruction-tuned models. The raw numbers here are genuinely staggering.
They really are.
The 72B base model achieves an 84.2 on MMLU. It hits an 89.5 on GSM-8K. And it scores a 64.6 on Human Evil for zero-shot coding.
To truly grasp the gravity of those metrics, we must contextualize them against the current open-weight landscape. MMLU, the Massive Multitask Language Understanding Benchmark, is a grueling test of zero-shot and few-shot knowledge across 57 distinct academic subjects, ranging from quantum physics to professional law.
Achieving an 84.2 doesn't just put it in the upper echelon, it surpasses human expert baselines in numerous specialized categories.
What is truly disruptive for practitioners is that it is decisively outperforming the leading 70 billion and massive 8 by 22 billion parameter open-weight models that have dominated the inference endpoints for the last several months.
It is showing distinct superiority, particularly in the strict logical domains of math and coding. An 89.5 on GSM-8K means the base model, before it has even been exposed to the DPO alignment phase to act like a helpful assistant, is almost flawlessly executing multi-step grade school math problems.
And the 72B Instruct version hits a 9.1 on MT-Bench.
MT-Bench uses an LLM as a judge paradigm to evaluate complex, multi-turn conversations, context retention, and subtle instruction following. A 9.1 signifies a highly coherent, highly aligned conversational agent that feels deeply intelligent to interact with. But I want to shift focus to the middleweights and the edge devices, because this is where the deployment reality for most developers lies.
The smaller models are incredibly important.
The 7 billion parameter model is punching so far above its weight class, it is distorting the baseline for its size category. It achieves over 50 on human evil and high 60s on MBPP.
The 7 billion parameter category is arguably the most critical battleground in the open source community right now. Its importance stems directly from hardware economics.
Hardware dictates adoption.
A 7B model is the largest architecture that can comfortably run in 16-bit precision, or easily fit in 4-bit quantization alongside a massive KV cache on a single, widely available 16-gigabyte consumer GPU. By dominating this specific category in coding benchmarks, it instantly becomes the default local coding assistant for thousands of independent developers and enterprise teams running local hardware.
Then you examine the inference economics of the 57B MoE. The MoE performs identically to a dense 30 billion plus parameter model across MMLU and coding benchmarks, but the inference latency is incredibly low.
That is the direct benefit of the fine-grained routing we discussed earlier. Because it only activates 14 billion parameters per forward pass, the memory bandwidth requirements, the HBM swapping that bottlenecks generation, are drastically reduced.
You attain the vast knowledge representation and nuanced reasoning capabilities of a massive 30B dense model, but the tokens per second generation speed feels closer to a standard 14B model.
It is the ultimate architectural compromise for enterprise users who possess robust hardware clusters but require ultra-low latency for user-facing applications. And the utility extends down to the 0.5B and 1.5B architectures.
I frequently see developers question the utility of a 0.5 billion parameter model. In an era of 70 billion parameter monoliths, a 0.5B model feels like a toy. What is the actual production use case for something that small?
The use case is absolute, uncompromised on-device inference. These models are engineered for true edge deployment: smartphones, smartwatches, IoT devices, or local routers.
Running entirely offline.
Exactly. A 1.5B model that has been trained on a highly curated, logically dense 7 trillion token dataset possesses incredibly strong foundational reasoning. It can act as a highly capable, entirely offline semantic router.
It can process incoming local text messages, parse calendar APIs, or summarize emails on a smartphone without ever transmitting a single packet of personal data to an external cloud server.
The privacy implications, combined with the zero latency execution, make these micro-models incredibly valuable for consumer tech integrations.
That offline, zero latency privacy is a massive selling point. Now, we have to address the long context evaluations, because this is the ultimate stress test of the dual chunk attention and yarn implementations. They evaluated the 131,000 token limit using needle in a haystack, needle bench, and LV-eval.
The standard needle in a haystack test visualizes retrieval accuracy across sequence length and document depth.
The resulting heat map for the 72B Instruct model is striking. It is essentially a solid block of perfect accuracy. It achieves near 100% retrieval of a single, highly specific fact placed at any depth from 0% to 100% within the 128,000 token document.
Historically, large language models suffer from a severe lost-in-the-middle phenomena. They maintain high attention weights for the absolute beginning of the prompt and the very end, but the attention entropy degrades the middle 50% of the document into a blur.
The fact that the model retrieves the needle regardless of placement proves that the yarn temperature rescaling successfully sharpens the attention logits across the entire 131K context.
But retrieving a single fact is essentially just a complex semantic search query. A simple embedding vector database could do that. To prove actual comprehension, we have to look at needle bench and LV-eval, which test multi-hop reasoning.
I want to push back on the compute cost of LV-eval. Running multi-hop reasoning over 128,000 tokens requires the model to hold multiple disparate facts in active memory and compute relationships between them. How does the model maintain coherence without the KV cache completely saturating the VRAM during these benchmarks?
That is exactly where grouped query attention and dual chunk attention harmonize. Needlebench tests the model by planting multiple distinct facts. Fact A at token 10,000, Fact B at token 60,000, Fact C at token 120,000.
The prompt forces the model to extract Fact A, combine it logically with Fact B to deduce a new premise, and apply that premise to Fact C to formulate the answer.
DCA ensures that the local chunk computations remain mathematically isolated, preventing the FLAW P count from exploding quadratically. Simultaneously, GQA compresses the massive 128K KV cache by a factor of 8, allowing the entire sequence context to remain resident in the GPU memory without constantly offloading to system RAM.
The model maintains high multi-hop accuracy precisely because the architecture prevents the hardware from bottlenecking the attention matrix. It's an incredible synergy of software algorithms and hardware awareness. Okay, we are moving to the final analytical segment: safety, contamination, and honest assessment.
This is crucial for open-weight models.
Whenever an open-weight model drops and aggressively dominates the established benchmarks, there is an immediate, healthy skepticism in the research community. The first question is always, did the model genuinely learn to reason, or did it simply memorize the test set during its massive 7 trillion token pre-training phase? How did the engineering team mathematically prove the integrity of their benchmark scores?
Data contamination is the most persistent threat to valid AI evaluation. To defend their claims, the team executed a highly rigorous contamination analysis pipeline. They didn't rely on basic keyword matching. They deployed strict 13-gram overlap filters alongside longest common subsequence, or LCS, algorithms.
Let's dissect those metrics. A 13-gram overlap filter scans the entire 7 trillion token pre-training corpus and the post-training datasets, looking for any sequence of 13 consecutive words that identically matches a sequence in the benchmark test sets.
And LCS removes all punctuation, capitalization, and formatting variables to expose deep structural string overlaps.
I'll play devil's advocate here. A 13-gram exact match is a strict filter. But what about semantic contamination? If a benchmark question was slightly rephrased in the training data, for instance, changing the variable names in a Python coding problem from X and Y to alpha and data, a strict 13-gram filter might miss the conceptual contamination. Did they rely purely on string matching?
It is a valid critique. And semantic contamination is notoriously difficult to quantify perfectly without utilizing compute-heavy embedding similarity models across all 7 trillion tokens, which is just unfeasible. However, their string matching approach was aggressively tuned to be overly sensitive.
So it flagged a lot of potential contamination.
They identified significant overlaps, but when they manually analyzed the flagged data, the vast majority were false positives inherent to the domains. In mathematics, standard theorems, proofs, and basic equations like the quadratic formula will invariably trigger 13-gram overlaps because there is only one syntactically correct way to write them.
And in coding, boilerplate setups, standard library imports, and basic algorithmic structures will perfectly match across millions of GitHub repositories. You cannot penalize the model's generalized reasoning capabilities simply because it was exposed to the fundamental laws of algebra or standard Python syntax during pre-training.
Exactly the conclusion they reached. However, to eliminate any doubt, they constructed a strictly non-contaminated sterilized test set.
They actively stripped out every single benchmark question that triggered the 13-gram overlap, including all the false positives.
They then reevaluated the models entirely on this sterilized dataset.
The critical finding.
The benchmark scores did not exhibit any statistically significant drop. The performance remained utterly robust. This provides highly compelling mathematical evidence that the model's superior scores are the result of generalized reasoning and complex latent representations, not rote memorization of the evaluation strings.
That exhaustive sterilization process is a massive validation of their data synthesis pipelines. But no architecture is without flaws. Let's analyze the safety evaluations and the author's own flag limitations. They ran extensive multilingual safety benchmarks covering illegal acts, fraud, and privacy.
The model demonstrates highly robust refusal rates for harmful prompts, often exceeding proprietary models.
But they openly highlight struggles with specific edge cases, particularly in pornography classification across their 30 supported languages.
This raises an important question regarding the linguistic complexities of global AI deployment. The team transparently admitted that while the safety alignments are highly effective in English, classifying explicit material becomes exponentially more difficult when dealing with the vast nuances of international slang, cultural idioms, and morphological structures in languages like Thai, Russian, or Arabic.
Differentiating between clinical, educational, or highly artistic anatomical descriptions versus explicit, harmful pornography is a complex semantic task. The DPO alignment struggles to maintain uniform strictness across 30 disparate linguistic latent spaces.
It is a stark reminder that safety alignment is not a perfectly solved mathematical equation. It is an ongoing, highly complex linguistic battle.
They also documented a specific limitation regarding the 7 billion parameter model's instruction following. Despite its dominance in zero-shot coding and math, the 7B model can occasionally drop constraints when subjected to highly complex, multifaceted prompts.
If you provide a prompt with 10 extremely specific formatting-heavy rules, it might ignore the 8th or 9th constraint, lagging slightly behind the absolute top-tier 8B proprietary models in rigid compliance.
That level of transparency is exactly what solidifies trust within the open-weight research community. They are not publishing a paper claiming artificial general intelligence or flawless execution. They are providing deeply documented, state-of-the-art architectures with clearly defined operational boundaries and identified areas for future optimization.
The technical honesty is refreshing.
Okay, we have reached the conclusion of our architectural breakdown, which means it is time for the Novel Notions segment.
I'm ready.
Just a quick note for the audience, this segment is purely for entertainment purposes only. We are engaging in speculative, scenario-based brainstorming based entirely on the technological trajectories discussed today.
Let's hear the ideas.
We are limiting ourselves to 2 highly specific, outlandish, but technically plausible applications based strictly on the capabilities we just unpacked. Idea number 1. Autonomous global bug bounty swarms. We discussed the 0.5B and 1.5B edge models, and we deeply analyzed the automated execution feedback loop used for synthesizing code preference data. What if we propose deploying millions of these 0.5B models on edge devices, idle laptops, old smartphones, decentralized servers worldwide, operating as a massive asynchronous swarm?
If we ground this directly in the established methodologies of the technical report, it is highly plausible. You integrate the execution feedback synthesis loop directly into the edge deployment. We established that the architecture natively supports generating code, writing its own Python verification tests, compiling the code in a sandbox, and learning from the deterministic execution results.
Imagine millions of these micromodels autonomously crawling open source repositories on GitHub 24/7. They actively scan the code bases for open issues, inefficiencies, or zero-day vulnerabilities. Because they are edge models, the centralized compute cost is zero. They utilize idle background processing on consumer hardware.
They read the repository, they hallucinate potential patches or security fixes based on their pre-trained logic, and then they use the verification functions to write unit tests against the repository's existing architecture. They compile it locally.
Precisely. 99.9% of the time, the micromodel fails. The compilation throws an error. But because you have a swarm of millions trying billions of divergent permutations, eventually, one isolated 0.5B model successfully compiles a patch that resolves a complex vulnerability and passes all verification tests.
The edge device then packages the mathematically verified code, the successful unit test, and the intermediate reasoning path, and transmits that highly curated, perfect preference data back to a centralized server.
This continuous stream of perfect data is then used to update and further specialize the 64 fine-grained routed experts of the massive 72B parent model. The edge swarm acts as an infinite autonomous data synthesis engine, constantly feeding mathematically proven solutions back to the mothership.
It creates a self-improving AI ecosystem. The tiny decentralized models act as the foragers, utilizing idle compute to discover truths, and the 72B monolithic model acts as the central repository absorbing the verified knowledge. I love it.
Let's move to idea 2, hyperlocal infinite cultural personas. I propose this technology signals the end of centralized English bias AI characters. We are moving towards a paradigm of perfectly localized infinite offline persona generation.
This extrapolation is deeply anchored in 3 specific architectural innovations we discussed. First, the 30-language native proficiency born from the massively expanded 151,000 token vocabulary. Second, the 131,000 token context window powered by dual chunk attention and yarn. And third, the data repurposing methodology, where the models synthesize perfect role-playing data directly from factual Wikipedia profiles.
So visualize a specialized application on your smartphone. Because the 1.5B model requires minimal VRAM, it runs completely locally on the device's neural processing unit. It never connects to a cloud API. You want to interact with a highly specific, historically accurate cultural figure, for example, a 12th century Arabic mathematician or a 19th century Vietnamese poet.
The application retrieves the dense factual Wikipedia profile and historical texts associated with that specific figure. Because the tokenizer natively comprehends Arabic and Vietnamese without fracturing the bytes and destroying the context window, it digests the entire cultural, historical, and linguistic nuance of that specific era perfectly.
The 1.5B model then executes the data repurposing methodology locally, instantiating a hyper-specific, historically rigid cultural persona directly in the device's memory.
And because of the 131,000 token context window managed by the DCA chunks, you can converse with this persona for weeks. It never suffers from attention entropy.
It stays flawlessly in character, maintaining the linguistic quirks, the precise historical worldview, and the deep cultural context of a 19th century Vietnamese poet for months of continuous, localized interaction. It completely shatters the current ecosystem where every AI assistant, regardless of the prompt, fundamentally sounds like a heavily aligned, polite customer service representative from a California tech company.
It mathematically democratizes cultural representation in artificial intelligence. The capability to generate infinite, highly robust, historically accurate personas that execute entirely on-edge hardware represents a profound evolution in global human-computer interaction.
It really does. So what does this all mean for the future of the field? We've unpacked the GQA memory bandwidth savings, the complex DCA matrix chunking, the violent 50% randomization of the MOE upcycling, and the self-synthesizing DPO pipelines.
We covered a lot of ground today.
But if we pull back and look at the macro trajectory, the most staggering revelation is the ablation study on the data ceiling. If 7 trillion tokens truly represents the asymptote for raw data volume, and if highly specialized, upcycled mixture of experts architectures running locally on consumer hardware are currently matching the performance of the massive closed API supercomputers from just last year.
Are we witnessing the definitive end of the scale is all you need era?
Exactly. Are we finally entering the era of hyper-curation, where the algorithmic elegance of the attention matrix and the strict curation of the pre-training data dictate performance far more than simply constructing the largest, most expensive server farm on Earth? It is a fascinating pivot point for the entire engineering community. Keep questioning the benchmark hype, keep analyzing the underlying architectures, and keep building.